Hello everyone, and in today's video we're going to build the AlexNet model architecture in PyTorch. In the previous video we took a look at the AlexNet paper and I tried to explain why the paper is important, why the model is so innovative and things like that. And I highly recommend you watch the first video first and then you watch this video to know how to implement this. But if you feel comfortable with the architecture and you want to see how it's done, you can watch this video too. So we're going to import torch and we're going to import torch.nn as nn. So first we're going to define the model. This will be class AlexNet. We're going to inherit from nn.module. Then we will create a constructor as always. We're going to need two parameters. First is in channels. It will be amount of channels that our image has. So for a grayscale image, we would have only one dimension, but in a regular image, we would have 3 channels RGB, which is probably the most common amount of channels. And number of classes is a pretty standard argument, which is going to be the amount of classes that we want to predict. Then we're going to call the super method. There are multiple ways to build the architecture. One of the ways would be to build 2 sequential models and then combine them. First would be the conv block and then the fully connected block. But I want you to understand how the layers are connected between each other. And I think it's a little bit easier to understand in a linear fashion that you're going to see it in a second. So first we're going to define all the convolutional layers. Let's call it conv1. It's going to be nn.conv2d. It'll accept 3 input channels, which we will pass here. Then as output, it will have 96 outputs, kernel size of 11, stride of 4, and padding of 2. The second layer will be 96 inputs, 256 outputs, kernel size of 5, stride of 1, and padding of 2. The third convolutional layer is going to have pretty much the same parameters. It's going to have 256 by 384, kernel size of 3, stride of 1, padding of 1 as well. We can copy it again. On 4 is going to be very similar. We're just going to change the input to 384. And finally, the 5th convolutional layer will be pretty much the same. We're going to change 384 output channels to 256. And this is it for our convolutional layers. Then we're going to define the fully connected layers. Call it FC1, fully connected layer 1. It's going to be nn.linear, and we're going to expect 256 by 6 by 6 input channels, input features, I should say. I'm going to explain why it is in a second. Let's first build all the layers, and then I'm going to explain why we chose this shape. This is going to output 4969 output features, I believe. Yeah. Then the second fully connected layer will be, let's change this to 2. It's going to take in 4069 input features and output the same amount as well. And the third layer will be 4069 by number of channels, a number of classes. This will be our final layer with number of classes outputs. So if we have 10 classes, it's going to output 10 values, and then we're going to apply softmax onto that to get the probabilities of the labels. And now let's add other layers, and not only layers. First, we will need a flatten layer, and then that flatten in order to go from convolutional layers to fully connected layers. Then we will need max pooling, which we will actually use a kernel size of 3 and stride of 2, which will allow us to do overlapping pooling as we saw in the paper. Then we'll need self.norm. It's going to be local response norm. The authors of the paper used size of 5. Then I believe k is equal to 2. We should not change the other values like alpha and beta, because the default values are the values that the authors of the paper used. And finally, we will need value as our activation function. And then that value, yep, that's pretty much it. Now let's build the forward pass. We will need to accept x as our input. And here we just are going to call all the layers. But after each layer, we'll apply self.value. After it, we will apply max pooling. We will apply normalization and then max pooling. Norm, and then we're going to finally call self.max pooling on that. Then the second layer is going to be the same. We're just going to change self.conv1 to self.conv2. Then the third and the fourth layer are not going to have max pooling, so we can remove that. And they're also not going to have a normalization layer. That's it. And we need to change this to 3. The fourth layer is the same almost. We'll change this to 4. And for the final layer, we do need to use max pooling. Max pooling, solve.value, solve.conv5 of x. Then we will solve.flatten it, and then we will call all the fully connected layers. Solve.value. Yes, actually, I just forgot. Thank you for the auto suggestions to add solve.dropout, which was used in the paper of probability of 0.5 of the neuron of being dropped out. So we will need dropout here. We will need self.value here, and come on, suggestions. Let's go. Yeah, this is it. This is the model that we have. Now I'm going to explain the shapes and how to calculate them, and why we multiplied this by 6 and 6 again. To calculate the output shapes of a convolutional layer, we need to take in the first amount of features that we're going to input to the model, which will be 224 as shown in the paper. So images of shape 224 by 224 by 3. We're going to subtract the kernel size from that, which is 11. Then we're going to add 2 times the padding, which is 2. And we're going to divide this by the stride size, which is 4. And we're going to get 54. This number is going to be floored, so we're going to round down to the lower number. So we're going to round it to 54 and add 1 to that, which is going to be 55. So the shapes after the first convolutional layer will be batch size by 96, which is the amount of filters that we're going to have. And then the other shapes will be 55 by 55 that we just calculated. But this is not all. So here we'll also apply ReLU, norm, and max pooling. ReLU and normalization layer do not contribute to the shapes, but max pooling does. For max pooling, the formula will be exactly the same. We will just calculate, we will take 55 as input this time, because this is the value that we got. We're going to subtract the kernel size, which is 3. And we're going to add the 2 times padding. Padding is 0 in this case, so we don't have to add it. And we're going to divide this by 2. And we're going to get to 26 and add 1 to that, which is 27. So the output shape after the first convolutional block is going to be batch size by 96 by 27 by 27. We can calculate the same thing for the second layer, which is, we'll just take 27 as our input. We're going to subtract 5 from that, which is our kernel size. We're going to add 2 times the padding, which is 1. We're going to get 24. We're going to divide it by 1, which is 24, and we're going to add 1 to that. Oh, you know what? Actually, the padding is 2 here as well. So our output shape will be 27. After that, don't forget about the max pooling layer. We're going to take 27. We're going to apply the same thing. We're going to subtract 3, which is our kernel size. We're going to divide it by the stride size, which is 2, and add 1 to that, which is 13. This is why our output will be batch size by 256, which is the amount of filters that we're going to output, 256, by 13 by 13. Now, I'm not going to calculate it for you here. If you want to do that, you can pause the video, calculate it yourself, and then check if you're correct. And I'm just going to pause the recording, and I will get back to you when I wrote down all the shapes. So here we got to the final convolutional layer, convolutional block, I should say. And after this, if you calculated everything correctly, you should have this shape. 256, batch size by 256 by 6 by 6. And now when we pass our outputs of the final convolutional block through the flattened layer, we're going to have 256 times 6 times 6, because flattened layer, what it does, it just flattens out all the values into one single long array. And the output will be batch size by 256 times 6 times 6, which is 9,216. And after that, it's very easy to calculate. We don't need to do any computations. We just need to know the output shapes of each of the linear layers. We know that it's going to be 4069 here. It's going to be the same here. You know what? Let's apply this dropout on each layer. So what I've done here, I just moved the dropout from being on a new line to just following the ReLU activation function after each of the fully connected layers. And for our final layer, we're just going to output batch size by number of classes. And this is going to be our output. So this is it for the model. Now we need to initialize the weights, because in the paper, as you might remember, they initialize the weights in a particular fashion. Here's a screenshot of that. And in order to do that, we can just create a function, call it init weights, let's say, and it's going to initialize the weights of the model. So I'm going to create a list. I'm going to call it bias1. And here I'm going to write all the indices of the layers, which need to be initialized with a bias of 1. So this is the first layer, the third layer, the fourth, the fifth, the sixth, and the seventh. And then we're going to go over all of the layers for I comma layer and enumerate self.that modules. So if you don't know what self.that modules does, it basically gives you a list of all the layers and their names in the architecture that you've specified. So we're going to go over all of them. We're going to get their index using the enumerate function, and we're going to check if is instance, is it a trainable layer? Because conf2d and linear layer are trainable and the rest of the layers are not trainable, like dropout, like normalization, like ReLU, max pooling, and flatten. And if it is true, we're going to also check if I in bias1, so we're going to check if the current index is in this list, and if it is, we're going to initialize bias with 1. And that's how we're going to do it. We are calling the init constant, and we're going to initialize the layer bias term with the value of 1. So if it's not in the bias 1 list, we're going to initialize it with the value of 0. And then that init constant, oh, here it should be a dot, layer.bias value is equal to 0. Next, what we need to do is we need to initialize the weights from a zero mean Gaussian distribution and with standard deviation of 0.01. So let's do that here, and then that init norm layer.weight. So here we are initializing the weights instead of the biases. We're going to initialize it with the mean of 0 and standard deviation of 0.01. This is pretty much it. Now let's test if everything works. Oh, actually, yeah, we need to call init weights here so that we initialize the weights in the constructor. So to test the model, we can create an object of our class AlexNet. We're going to have 3 input channels and 100 classes. And let's create some artificial inputs. X is going to be equal to torch. We're going to have 64 images in our batch size, 3 channels by 224 by 224. It will just randomly generate numbers from a normal distribution to fit in these shapes. And now if we just call print model of X, we should get 64 by 100 if everything's correct. Let's see that. Okay, something is not correct. Object is not callable. Okay, you guys, I found the issue. It's very basic. We should just remove the commas here because we're not creating a sequential model. We're just initializing the variable names, instance variables in the class. So it was a very basic issue, and now we're going to run the model again, and hopefully we're going to get the good result. Not again. So I found the issue again. Instead of norm, we should have normal and underscore. So yeah, and also I printed out the shapes here. And now let's see if it works. Yes, and we get the correct output shapes of 64 as our batch size and 100 number of classes. So this is pretty much it for the implementation. In the next video, I'm going to show you how to use the AlexNet model to train it on a dataset of 100 classes. This is going to be a sports dataset. We're going to classify 100 classes, 100 different types of sports. And you're going to see how to use this model to fit it on real world examples. So that was it. Thank you for watching, and I hope you enjoyed the video.